In this video, we'll go about coding up the solution that was presented in the previous video, a link of which appears here. And the first thing that I'm going to do is put some comments in terms of how we're going to solve this. The first is to set up the parameters. Then we'll set up our matrices. Then we'll find the natural frequencies and the mode shapes. We'll then numerically integrate the equations of motion. And then finally we'll plot the results. Alright, so let's put some meat into this. First of all, we need NumPy. We're going to need the sine function, so we'll say from math import sine. Oh, I need a line here. What else? We need the eigh function, which solves the eigenvalue problem. So from scipy.lim algebra import eigh. And I think we need the inverse function too. So from numpy lim alg import inverse. And then since we'd like to plot some things at the end, we want matplotlib. So from matplotlib, we'll import pyplot. We'll call that plt. Alright, so the first order of business is to set up the various parameters that we were given in the last video. F0 is equal to 5. Omega, which is the frequency of the forcing function, is 10. The stiffness of the springs, they're all the same, that is 1,000. M is given as 1 kilogram, and the degrees of freedom in this problem with 3. And that's it for the parameters. As far as setting up the matrices go, the first thing we want to do is define our stiffness matrix, K. K is a NumPy array, and it's a 3 by 3 matrix. So how do we want to do it? Okay, and the first row is 3 times K, minus K, and minus K. The second row is minus K, K, and 0. And the third row is minus K, 0, K. Similarly for the mass matrix, and we'll call this capital M, it's a NumPy array. And the same thing, we want a 3 by 3, so let's put in 3 rows here. The first row is 2 times M, 0, 0, since there's no coupling in the mass matrix. All the off-diagonal terms are 0. Second row is 0, M, 0, and the third row is 0, 0, M. And that's it. And the other thing I'm going to set up is the identity matrix. And the way we do this in NumPy is just NumPy identity. And since it knows it's square, we actually just need to put in the degrees of freedom. In this case, it's a 3 by 3. Right, and then following on from our last video, we want to set up the matrices that we generated when rewriting the problem in state space form. These matrices we called A and B. So A is, it's a NumPy array again. And, well, we want to start off just by creating a matrix full of zeros, and then we'll go about populating it. So I'll say NumPy zeros, and it's 2 DOF by 2 DOF. Remember that these matrices are 2n by 2n, and I've put NP here twice. I need to remove one of those. We can do exactly the same thing for B, so I'll copy and paste this. Just change that to a B. Our state vector Y is, we'll do the same thing, except it's a vector. So it's 2 DOF, or 2n by 1. And exactly the same thing for our force vector. Capital F is the same dimension. Okay, now again from the last video we showed how we create the A matrix. The first n by n columns and rows of the mass matrix, of the A matrix, is just the mass matrix. So we write this as follows, from 0 to 3. Just remember that 3 is not inclusive in Python indexing. So this would be rows 0, 1, and 2. That is the first 3 rows. And columns 0, 1, and 2. Same thing. And that's equal to the mass matrix. And then the other thing that we need to put into the A matrix is in the bottom right n by n portion of it. That is 3 to 6. Remember, 6 is not inclusive, so at index 3, 4, and 5, bearing in mind that Python starts at a 0 index, we want the identity matrix. If any of this is confusing, just click on the link to the right and it will take you back to the last video where we derived this. And similarly for the B matrix, we'll say that B, in this case, it's 0, 3, and 3, 6. And that is equal to the K matrix. And then in the lower, in the lower portion of it, which is 3, 6 by 0, 3, that would be the negative of the identity matrix. Okay, and that's it. A couple of other parameters I want to put up here at the top is the time step that we're going to use. We called delta t in the past video. And I'm going to make this 10 to the minus 4 seconds. So 1.0 e minus 4. I don't really want to get into how we determine our step size now. But I'd like to mention that if your step size is too big, you're going to get garbage results. If it's too small, it's going to take too long. We'll worry about that in a future video. For now, let's just assume you can use 10 to the minus 4 as an appropriate time step. And we want the end time. In other words, we're going to start at time equals 0, but when are we going to end? And for now, let's just say the end time is 4 seconds. Okay, that's all good. Oops. So the next thing we want to do is find the natural frequency. I'm just going to run this and make sure we have no errors quickly. Shouldn't really do anything except set up these matrices, but it's a good time just to check that. Error, NP is not defined, so, top line, I should have imported numpy as NP, and there we go, it's finished. So that all works. So the first thing I want to do in terms of calculating results is I want to find out the natural frequencies and the corresponding mode shapes. And for this I use the IH function. I put in K and M in that order, and it's going to return the eigenvalues and the eigenvectors. So we'll catch it as follows, evals and evex. Then we want to convert the eigenvalues into frequencies, and we know that that is just the square root of the eigenvalues, NP QRT. By the way, by using the numpy square root function, it actually works on an element by element fashion. So I just need to do it like that, and then I can go print frequencies, and I can print the eigenvectors. So lo and behold, when we run that, we get that the natural frequencies, there are 3 of them, of course, because it's a 3 degree of freedom problem. 14.8 would be the fundamental frequency. The next one is 31.6, and then finally the highest frequency is 47.757. These, looking vertically, are the mode shapes corresponding to each one of these natural frequencies. All right, so we'll continue by numerically integrating the equations of motion. Make a little bit of space here. All right, and what I want to do here is say for t in, we'll use the numpy a range function to set up the time steps, well, the time intervals, I should say. It goes from 0 to n time, and in intervals of the time step. The first thing we need to do is create the forcing function. That was given as f0 or f0 times sine of omega t, just like that. Okay. Let's see, and we want to put that into this force vector here, the state space version of this force vector. And you might remember that it actually goes in the second row, or the second position in the vector. And because Python is zero-based indexing, it's actually f of 1. F of 1 is the second row because f of 0 is the first row. All right, so we've created that now. And the reason we're doing that inside the loop is because it's a function of time, it's going to happen continually. One of the things we can do outside of the loop, because we don't want to do it every single time, it only needs to be done once, is to find the inverse of the mass matrix. Let's see how we want to do this. Not the mass matrix, but the A matrix, the state space version of the mass matrix. We'll call it A inverse, and that is equal to the inverse of A. I think that's easy enough. And by the way, inverting a matrix is quite a CPU-intensive process. Not a big deal in the case of a 3x3 matrix, but if you only have to do it once, we don't want to put it inside the loop and have to do it every single time. That's only going to slow things down. In addition, I want to create some lists here to capture the results. We'll say force is equal to a list. And then the various coordinates that we want to capture, x1, x2, x3, and we'll just keep adding the results to this list as we calculate them. All right, so we have our forcing function. What is the next step? It's just to apply the formula as we derived in the last video, that y at time plus 1, which we'll call y new, is equal to y at t, which we'll call y, plus delta t, which is the time step, times A inverse dot, because we're multiplying in the matrix sense, and this is f minus b times y. So we'll write that as f minus b, and the times again is a dot, because we're multiplying matrices or matrix and a vector, and this would be y. Just leave a space there to make it clear. So this is exactly the equation we saw in the previous video, where I'm calculating the difference in effect between the forcing, the external force, and the spring force, or spring forces. I'm going to multiply that by A inverse, multiply it by the time step, and then add that to y to get a new updated value of y new. Then I need to make sure that y is now equal to y new before we proceed to the next step. And that is it. The only thing that remains to be done before completing this loop is to actually store some of our results. So force, in this case, we won't do append but extend so that we can flatten out the list into one big list. And this is F, I'm just storing the actual force itself. The whole forcing vector is 0 except for this component here. So I'm just doing that so we can examine it and make sure everything looks right. I'm going to do the same thing for x1. And what is x1? Well, we're going to take from the y vector. Remember that the y vector is just the velocities and the displacements stacked one on top of the other. So it's a 2n vector. The first n rows are the velocities, and the second n rows are the positions or displacements, I should say. So actually, it's 3. The fourth one, which is the third index, is x1. And I can do the same thing for x2 and x3. In this case, it will be y4 and y5. Okay, and believe it or not, we are pretty much done with this. Okay, the rest of it I'll do just for plotting purposes, but let's just see if it runs, even though I'm not outputting anything new yet. Okay, everything runs, no mistakes. So now what we want to do is create the data to be outputted. We've already got the displacements and the forces. What we need now is the time. The time is here, but we didn't store it. So let's do that now. We'll do this Pythonically. So we'll say for t in np, oh, that's just this. For t in, take this. And now in Python, what's really neat, we can turn that into a list shorthand by putting square brackets around it. And what are we trying to get here? What we're trying to get is t, and we'll say time is equal to this. All right, so what I've done is I've created a list that I'm calling time, and what that list is just the time t for each t in this range, which is exactly what I did up top here when I generated it, but I didn't store it. All right, and in fact what I'm going to do is, just so I don't get decimal places, because there sometimes are rounding errors, I'm just going to round time here to, well, 5 decimal places. And now we're going to plot it. So we take plot, this is pyplot, plot, and what do we want to plot? We want to plot time versus x1. That's easy. We also want to plot time versus x2 and time versus x3. And this should actually be down here. And then the last thing that we need to do is actually just show this. In addition, I'm separately going to plot on a separate chart the force. Well, plot.plt.plot time versus force, and plt show. Let's have a look at what we've done. Running it. PLT is not defined. Oh, I called it plot. Here at the top, I put PLOT instead of PLT. Let's run it again. And I need to minimize this a bit so that I can bring it onto the screen. And here is the plot. Oh, and I just killed it. Let me run it again quickly. And there we go. So why do I only see 2 pieces of data? Perhaps the one is lying directly over the other one. Oh, no, it's because here I've got 344, not 345. So we're going to run this again. And there we go. We can see our displacement for each of the 3 masses plotted in different colors. We can see that our maximum amplitude is somewhere around here. It's about 0.027, that's meters, so it's about 27 centimeters. And I think we can just dress this up a little bit by putting a legend and some labels on it. Separately, I want to show you what the forcing function looks like. That's the second plot, this one over here. Pretty much what we expected. It's got an amplitude of 5, and you can see based on this frequency at the top, the frequency of 10, this is what's going on. Interesting to note that we assumed that the initial state vector was 0 velocities and 0 displacements all around. And we know that the fundamental frequency is 14, but we're oscillating, we're forcing it at a frequency of 10. So we don't expect to get resonance, and you're seeing that in the charts. Let me just add a bit of labeling here, might make it a little bit easier to see. PLT X label, we'll call this time in seconds. I think it's always good to put labels on your charts. The Y label is the displacement, and that's in meters. We should give it a title. We'll call these response curves. And I think we can add a legend that will also help us see which one is which in terms of the colors. So the legend would be, oh, how do we do this? It would be the different entities. So it would be x1, x1, x2, and x3. And then we want to say what the location of the legend is. We can put that at, let's just say, the lower right. And let's have a look at that. Oh, I did something wrong here. Plot, oh, I left out the word legend. Thank you. Plot legend. These are the different curves that I want the legend for, and this is the location of it. So now when I run this, I should get a much prettier looking curve. Indeed I do. And you can see from the color code that the blue curve is x1, the green curve is x2, which is actually the mass that I'm forcing, mass number 2, and then the red one is x3. Bearing in mind that the blue one is the bigger mass, that's the one that weighs twice as much as the other two. So another thing I thought I would do is, just because it gives a bit more understanding, is let's try to force it at its fundamental frequency and see what happens. Bearing in mind again what it looks like at something other than its fundamental frequency is a response like this, where it seems to be a little bit all over the place. It grows and then it dies out. Now if we change this from 10 to the exact frequency and we run it, you can see that the displacements just continue to grow. And here's what's interesting is when you oscillate it at this frequency, all of these are in harmony. All these different displacements you can see. The blue one, which is the bigger mass, does not displace quite as much as the two smaller masses. But even though you're tugging on the green mass, the red one displaces roughly the same amount. And you know, we can run this a little bit further. Instead of stopping at 4 seconds, we can run it all the way to 10 seconds, just to make the point. And here's what happens. It just starts growing. Interesting. And if you look at this mode shape, this is the first mode, you can kind of see it here. It's saying that all of these are displacing in the same direction by roughly the same amount. Of course, mass 1, which is the top one, is displacing a little bit less than the other two, and you can see that graphically. So that's what the mode shape is kind of telling you, is the relative displacement in that mode of each of the masses. Okay, so what happens if we run it in the second mode, and what would we expect? In the second mode, we see that there's a negative here, and we also see that this is way smaller than the other two. All right, so can you imagine what that's going to look like? Let's run it and find out. Okay, so again we get resonance, but it actually looks like a different type of resonance now. If you compare this to the previous curve, first of all, the blue mass, the mass number 1, which is the blue curve, doesn't really displace all that much. It's actually the other two that start going out of whack. And notice that they are completely out of phase with one another. Right? So the green and the red curves are displaced by the same amount, but in opposite directions. The one is going up and the other one is going down. And again, you can see that from the mode shape. The one is just the negative of the other, and then of course mass number 1, which is this top one, is about 15 orders of magnitude less than the other two. All right, so what do we think is going to happen in this last mode? Well, in this last mode, it seems that these two masses oscillate together, mass 2 and mass 3, but it seems that mass 1 is oscillating opposite. It's completely out of phase with those two, and it is growing even quicker. So let's try to run that. If we take this frequency, we pop this in at the top, we run it, well, you're kind of seeing that now in the plot. The blue is clearly bigger than the other two. The red and the green curves tend to be in phase with one another, and the blue curve is completely out of phase with the other two. Anyway, so hopefully you learned something useful from this. I try to keep the code somewhat general, that you could use it for bigger multi-degree of freedom systems. But this is a good example of how to calculate something numerically, a numerical solution to a problem that's very tough to work by hand. And it really didn't take us that long to code it up. The code it's not even 70 lines of code. So I hope you found something useful in this video. If you did, please go ahead and give it a thumbs up. That way others get to see it too. Thank you for watching, and we'll catch up with you in the next video.